So here we're looking at our third important proof of this section. We want to let H be a subspace of a finite dimensional vector space V. Any linearly independent set in the subspace H can be expanded, if necessary, to a basis for the subspace H. Also, H is finite dimensional, and the dimension of H is always less than or equal to the dimension of the vector space V. So we need to look at the proof for this. So we want to start with two different cases. Let's begin by supposing that the subspace H here is the zero vector space. So this is the cute set. We can say, well, we know that the dimension of the zero vector space is 0, which is going to be less than or equal to the dimension of the vector space V. Oops, we did it. So now let's think about a more arbitrary case here. Let's suppose that a set S is defined by the set of vectors v sub 1 through v sub n. And so we need to think about two cases here. We need to think about if this set spans the subspace, and then what happens if it doesn't span the subspace. So case 1, if this set S spans H, then we automatically have a basis. And we're all set. So now we need to think about the case where if S does not span H. So if S does not span H, then we can simply add another vector to the set S and expand. So here we go. Then we want to add another vector to S and expand. So we're taking that originally defined S, or the originally defined set v sub 1, all the way to v sub n, and now we want to add another vector to this set. So we'll say vector v sub n plus 1. And expanding this out, we now have the new set v sub 1 all the way to vector v sub n plus 1. And this is linearly independent. So just like we did before, we now need to think about, okay, well, does this new set S span H? Right, so if our new S spans H, this lets us know that we have a basis. But what about if it does not span H? Well, we have a solution to that. We'll simply repeat this process that we just did here until we attain a set that does span the subspace. So again, if our new set here does not span H, we simply repeat this same process until we attain a set that does. So then the last thing that we need to consider here, but how do we know that the dimension of the subspace is going to be less than or equal to the dimension of the vector space? So you want to keep in mind here that if we keep expanding, eventually we're going to reach a point where we have a basis. And since we're pulling vectors from our vector space V into the subspace H, if the vector space has a set of n linearly independent vectors, then the subspace can never get a set of vectors greater than n. So, again, if we keep expanding, eventually we get a basis. So if we keep expanding, eventually we'll reach a point where we have a basis. And now since we're pulling vectors from the vector space V, So since we are pulling vectors from V into the subspace H, if a vector space V has n linearly independent vectors, then H can never get a set of vectors greater than n. So then the subspace can never get a set of vectors greater than n, which confirms that the dimension of the subspace H will always be less than or equal to the dimension of the vector space V. And we have finished our proof.